All right, going to go ahead and get started here. We are at the end of week 7 in geometry, and we're talking about polygons. Tuesday, we talked about interior angle sums and exterior angles and regular polygons and how to find the degree measurements of angles in a polygon, no matter how many sides there are. So today gets into something a little bit different, but it's kind of an expansion of that from the standpoint that there are some specific properties that polygons share. And so those are the things that we have to pay attention to when we're working with some of these shapes. So, and the first one here in the packet, your study packet, is about parallelograms. You guys know anything about parallelograms? Okay. Parallelogram, you can see in the directions for those first problems. It's also called a quadrilateral. Quadrilateral means 4 sides. Parallelogram is essentially, if you took a rectangle and took one of the corners and just pushed the corner in to tilt the rectangle over. I mean, I think you can probably visualize that from looking at this first example here. And parallelograms have reliable properties that anytime you see a parallelogram, there are some things that you absolutely know. One of those is the fact that you've got, like a rectangle, you've got 2 pairs of sides that are parallel. Well, that's why they're called parallelograms. They're not called rectangles because they don't have 90-degree angles. Parallelogram, though, has 2 pairs of parallel sides. So if you look at this first example here, it's giving you the side lengths of AB and BC. Well, automatically, you know, DC is going to be the same as AB, and AD is going to be the same as BC because of those properties. So there's not a whole lot more to parallelograms. There's 5 properties that are going to be listed here. Does anybody know why that they would list 68 degrees here as this angle for D? How does that help us find the other angle measures? I mean, the reason I'm asking these questions, because these are the kind of questions that hopefully you're asking yourself as you go through these problems, because that's kind of what the thinking process needs to be. Why is that information there?
Because it used to be a 90-degree angle.
What? Used to be what?
A 90-degree angle.
Well, if it was a rectangle, it would be. But that 68 degrees is there to help us figure out all the other angles. Think back to your parallel lines and transversals, right? There are some things that you can rely on when you've got parallel lines, into alternate interior, alternate exterior, that sort of thing. So parallelograms, the opposite angle, the opposite corner is always going to have the same measurement. Any 2 consecutive, think about consecutive interior angles. What do they total from the parallel lines and transversals unit that we did? They total 180. Same thing here. Any 2 angles in a parallelogram are going to total 180. So it doesn't matter if you take D and C or D and A or A and B. I mean, you just go around the parallelogram. Any 2 together, any 2 angles together are going to total 180. So that allows you to figure out what C is, or A, because A and C are going to be the same. Opposite corners are going to be the same. Consecutive corners are going to total 180. So let's look at the written out properties here so you can get these in your notes. And we're going to be looking at a bunch of different types of shapes for the rest of this packet. Opposite sides are parallel. Opposite sides are congruent. Opposite angles are congruent. Consecutive angles are supplementary. Now, in the triangles exam, I was still seeing some people mixing up supplementary and complementary. Supplementary totals 180. Complementary is only 90. So don't be thinking that these angles together are going to total 90. Supplementary is 180. One that may seem a little bit odd is the last one. Diagonals bisect each other. Diagonals bisect each other. So problems 3 and 4 include the diagonals. The property tells us that diagonals bisect each other. So how would, in problem number 3, how do we use the information that's given to us to find the length of VS, for instance? It's one of the things that's listed here. It's asking us to figure out what VS equals.
What's 7, isn't it?
Yeah, exactly. I mean, it's kind of a no-brainer, really, because if this line here has been bisected by the other diagonal, you got SU here going from corner to corner, RT, well, they both bisect each other. So UV has to be the same length as VS, because what does bisect mean? It cuts it exactly in half. And they've given us one of the dimensions, which is half of that line. So it also asks us to figure out what VT is. How do we do that? Look down below the parallelogram, the little asterisk tells us that RT equals 30.
15.
Yeah, 15, exactly. And I'm bringing that up especially because on some of these tests, it's almost like people aren't using all the information that they're given to solve some of the test questions, and we're trying to force an answer to fit the diagram. Well, that's not how geometry works. We have to use, and we can only use exactly what we're given, or what we can prove. And it's especially true on those the similarity proofs. Hardly anyone did a very good job on those, because, you know, and I'm backtracking a little bit here in case you're thinking about redoing that test. You know, if the triangles that they're showing you only have dimensions on the sides, the only possible proof is side, side, side. There's no way to have angle, angle, or side, angle, side proof. It's just impossible if you don't have any angle measurements. But I saw answers like that. trying to force a proof onto a drawing. And by the same token, if you don't have any side measurements and all you have are angle degrees, you can't have side, 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 or any proof that involves the sides. This is kind of related to that because I need to use these properties. I got to use these properties in order to be able to figure out how these problems can be solved. And the diagonals bisecting each other is a really important piece there for number 3. Number 4, if you look at the answered number 4, there's opposite sides parallel, opposite sides congruent, opposite angles are congruent, consecutive angles are supplementary, diagonals bisect each other. So what do we have? Okay. Only thing I see are angle measurements. We have no side lengths. They're not asking us for any side lengths. Again, below the drawing, there's a little asterisk. It says the measure of the angle FED is 134 degrees. So how did they get the measure of angle DEC? How did they get 63 for that? Well, drawing gives you 71 degrees as part of that large angle FED. That's why you need the asterisk information at the bottom of that drawing, because the overall angle is 134. So what's 134 minus 71? 63. Then you can start looking at, and there's a little star below that that's been handwritten in here. Alternate interior angles. Why would that be on here? Because we're talking about parallel lines. The sides of parallelograms are parallel. So if you start cutting through these angles, now you've got a transversal that's going between two lines that are parallel. So automatically it sets up the potential for alternate interior angles and maybe even consecutive interior angles. So what are you going to do with problem number 5? Given that xy is 15, wx is 22, zx is 52. We got a bunch of different information there.
And WZ is 15.
WZ. Yep. I agree with that. Because you saw right here in the givens that XY, the opposite side, which is parallel, is already given to us as 15. So parallel side has to be congruent. Good.
ZY is 22.
ZY, okay, ZY is the bottom part of the parallelogram. So then we're looking at WX. Yep, there you go. That's easy enough. So I don't know if you other ladies are paying attention to this or not, but what Jonathan's doing is going down this list of the blanks over here and identifying. I don't know, are you doing this on paper, Jonathan, or are you just trying to do this in your head?
I'm just doing it in my head.
Okay. Because if it's me, and you know, and maybe this is what you would do if you're at home, I'm going to start labeling. Okay, XY is 15, so I know that. WX is 22, I know that. I can write that 22 there. ZX is the diagonal all the way through there. That's 52. WT is 23. Okay, so now I know all the side lengths and the diagonal lengths, right? Because the diagonals bisect each other. A problem like this has got 8 different things that's given to you would be a perfect one to do all that labeling. Because how do you figure out what TX is? Okay, here's TX.
52 divided by 2.
Yeah, it's exactly right. It's half of the overall length of that diagonal. So it's kind of what you're going to have to do in all these sorts of parallelogram problems. And there's not a whole lot more that they can really do to them other than give you those pieces of information in different ways, either the side lengths or the angle measures or both. Problem 6 only gives you the angle measures. GHF, 34 degrees, okay. So GFJ, if that's on here, GHF, sorry, JFH is going to be the alternate interior angle. That's going to be 34 degrees as they ask us that. H or JFH. And here it is. It's written back the opposite way, but it's the same thing. HFJ, opposite this angle right here. Can't draw a shape there, but it's opposite that angle. Alternate interior will be over here in that angle. So it's not just using the properties that they're listing here for parallelograms. You can see that already in some of these answers. You got to remember that when we have parallel lines, it sets up some specific relationships between angles, especially when you start cutting through them. And that those other definitions from that parallel lines and transversals chapter are going to come back again and again. Anybody have questions? Okay, the next page here. Okay, now they're going to try to make it more difficult by adding some algebra to it. We got some algebraic expressions. So now you're going to have to set up some equations in order to be able to solve for x. Those first two look pretty easy. Which one of the properties are you going to rely on to solve these first two? Opposite sides parallel? Okay, well, I got opposite sides. Man, they look parallel. That doesn't help me. I don't have any angle information, so I don't care that they're parallel right now. Opposite sides are congruent. Probably need that one to set up your equation. Right? Opposite sides are congruent, so LM has to equal PN. So 9x minus 25 equals 5x plus 7. Same thing over here. These are opposite sides. WX is opposite ZY. Those are going to be equal to each other. They're congruent. Piece of cake. Make them equal to each other. So how do we solve a problem like 9 or 10? If TV is 74 and WV is 4x plus 1. Does TV equal WV? Nope. Which property are you going to use? Right now, problem number 9 seems to revolve all around this part of that parallelogram. So we're not talking about opposite sides anymore. And again, this is where you need to keep that list of the properties. And you guys have heard me say this over and over and over again. Write this stuff down. Put it in your notes. Take a picture of it. Something. Don't try to memorize this. Don't try to follow this along and expect to be able to remember it when you sit down and do these problems or have a test, because it's just not possible. There's too much here. Too many properties, too many definitions for anyone to remember. Now, like I said, Tuesday, I know all this stuff because I've done it thousands of times. Don't expect you guys to be able to do that. But what I expect is that you're going to be able to look at a problem like this and realize, okay, here's the properties for parallelograms. I don't have opposite sides here because the example here doesn't even involve the sides. It only involves this one diagonal, TV and WV, which is a part of it. I don't have consecutive angles. We're not even talking about angle measures, right? It's links. These are links of that on that diagonal. So the only property that I can use to solve this problem is number 5. It says diagonals bisect each other. So how do I use that to set this equation up? To find x. You're going to see some problems like this on the test where you're going to have to do these calculations. You're going to have to be able to set up your own equation and solve it for x and get the right answer. It's not that complicated. You have to be able to apply this property. Diagonals bisect each other. I see a diagonal here. I see another diagonal here. What's the relationship between TV and WV?
They're both halves.
They're not both halves.
Or WV. WV is half of 74.
Thank you, Jonathan. Excellent. Yes. So how can I set up an equation knowing that? If WV is half of TV, can we divide TV by 2 and say that it's equal to 4x plus 1? Wouldn't that be half of TV?
Answer is 9. 9x. Or x is 9.
That sounds correct. I'm going to pause this for a moment here. So here I've got this particular problem set up now with the properties there as my reminder. Like I talked about a minute ago, what properties apply that are going to help me solve this problem? Opposite sides are parallel. Well, TV and WV, those are not sides at all. So that doesn't help me. Opposite sides congruent. Well, again, they're not sides, so it doesn't help me either. I don't have any angle information, so opposite angles are congruent is worthless on this problem. And so is property number 4, consecutive angles are supplementary. I don't care right now because we're not even talking about any angle information. So the only property that's applicable is the 5th one. Diagonals bisect each other. SU is one diagonal, TV is the other diagonal, and they cut each other in half. That's what bisect means. It's what it always means. So TV, this length here, is 74. WV, which is this length, is 4x plus 1. So clearly they're not equal to each other. And the question I asked before was, can we take TV, divide it by 2, and say that it is equal to 4x plus 1? Well, why would I divide by 2? Because the property tells me diagonals bisect each other. I got a line cutting through that TV diagonal by another diagonal, so it's cut it in half. Automatically, I know that WV is half of TV, or said the opposite way, TV is twice of WV. So if you don't like that structure, then multiply WV by 2. 2 times WV. Okay, now we know that WV in this case is 4x plus 1. Okay, put it in there. So it doesn't matter which way you write this. Jonathan's already figured out that x equals 9. Because if you write it this way, if you write it this second way, what's the first thing that you're going to have to do? First thing you should do?
Distribute.
You could. It's not what I would do. I'm going to divide both sides by 2. That way I don't have to mess with the distributive property. And look what you get. You get the other equation. If you did the distributive property, though, there's nothing wrong with that. So 74 equals 2 times 4x plus 1. Do the distributive property, 74 equals 8x plus 2. Take away 2 from both sides, you got 72. 72 equals 8x. Divide both sides by 8, you got x equals 9. So all the problems that you're going to see in this unit are about applying the properties. Does that help? Elvia?
Yeah, a little. Sorry, I'm writing down the properties of parallelograms.
Yeah, you said it helps a little. What are you still struggling with?
Okay, so I think I would like need to see another excuse me. I think I would like to see another problem like that to actually get a clue of what we're doing.
Good, number 10. It's not exactly like that, but it's similar. If ns equals 2x plus 7 and sq equals 5x minus 23, find nq. Here's our problem. NS is 2x plus 7. So it's right here. SQ, 5x minus 23. That's here. Again, we're talking about diagonals, so the only property of this for this problem that we give a darn about is that the diagonals bisect each other. So that automatically tells me that this diagonal here bisects that one and vice versa. So they cut each other in half. So NQ is the whole length here. It's from here to here. So what do you do with those descriptions that they gave us for NS and SQ? First thing we got to do is find X. So how are you going to find X? I don't know what anybody else out there is doing except for Elvia and Jonathan, but you guys should be chiming in here with some kind of response, because maybe you already got this mastered. I kind of doubt it. This is the only property we care about. We don't have sides. We don't have angles. We have diagonals. So how do we set this up to find X?
It says 2x plus 7 equals 5x minus 23.
Hallelujah. Thank you.
Oh my God, I was going to say that, but I wasn't sure. Dang it. Sorry.
You got to say something. I don't care if it's wrong. It doesn't matter. How you going to learn this unless you make some mistakes? You're going to learn more from making mistakes on this than you will any other way. So that's going to allow us to figure out what X is. This is straightforward equation solving. We've got a one variable equation, get the X's together on one side, get the constants together on the other, and away you go. So once we found X, we still have this second part of the problem here. How do we find what NQ is? Now, each of these are equal to each other. So there's a couple different ways you could go about finding NQ. You can add all those together. 2x plus 7 plus 5x minus 23. All right. Each one of those is half. So when you combine them, you got the whole, right? You got two things, two halves, put them together, you got the whole thing. NQ is the whole thing that we're talking about. That's one way to do it. You still need to know what X is. So you still have to do the first step, which is this one. So I'm going to subtract 2x from both sides. Seven equals 3x minus 23. Add 23. $30 equals 3x. X equals 10. Okay. Now I know what X is. So I'm going to be lazy and just figure out what one of these halves totals. So NS is 2x plus 7. That's half of it, right? 2 times 10 plus 7 equals NS. So 27. NS is 27, so NQ is 54. How do I know that? Well, we already established that these two here are equal to each other. So if this one is 27, then this one has to be 27 also. 27 plus 27 is 54. And I was able to do all that because I know that diagonals bisect each other. The words set up a relationship within the shape. The relationship is between the halves. It creates halves. We know how to deal with a half. A half and a half equals a whole. You take a whole and you divide it in half, you got two equal parts. That's all we're doing here. And then using the algebraic expressions to fill in the blanks on those equations and putting those relationships into an algebraic equation. And every problem in this unit is going to be like that. What is the property that I'm working with? What is the property I'm working with? For parallelograms on these two, only thing we care about are the fact that we got diagonals cutting each other in half. What properties are we going to look at on 11 and 12? We don't have any side information on 11 or 12.
Corresponding angles.
Corresponding?
Or no.
Opposites. It's this one, the third, number 3. Opposite angles are congruent. You got the right idea, I'm pretty sure, but I think you maybe just used the wrong term there, Jonathan. So these angles here are congruent. They're going to be equal to each other. 12 is a little different because 12 now gets into consecutive angles, supplementary. So 11's got two angles that are going to be equal to each other. 12 has two angles that are going to total 180. Remember, that's what supplementary means. Be total 180. They're consecutive because if you start at Q and just go around the parallelogram, P is the next one that you hit. It's consecutive. If you were to straighten out that whole thing into a straight line, it goes and start at Q, it goes Q, P, S, R. That's consecutive. What do you hit next? Again, it's just identifying the property that's applicable. So practice those remaining problems if you need to and send them to me. Fortunately for you guys, this next page, which is shown up in the corner as homework 29. We're not doing this as homework. But with parallelograms, how are you going to prove that you have something that's a parallelogram? Again, these are proofs similar to, with triangles. The proofs that we had were for congruency. There's 5 different ones. For similarity, there's 3 different ones. There are 3 methods to prove that parallelograms are actually parallelograms. And if you do it with the ordered pairs of the corners and you plotted them on the coordinate plane, then that allows you to take one of these 3 methods and determine if they are congruent or not. So if you look at that first method, it says prove both pairs of opposite sides are congruent. If you can imagine this parallelogram here drawn on XY coordinate plane, we got parallel lines here. What's the rule for parallel lines when we graph parallel lines? How do we know we have parallel lines?
They don't ever touch.
Yeah, but what is it about an equation for parallel lines that tells us they are parallel?
Is it the x-intercept or the y-intercept is 0?
No, doesn't have anything to do with the intercepts. The intercepts are going to be different with parallel lines. What's going to be the same?
I'm guessing here, but the angles.
All I'm talking about are parallel lines from the unit on slope. We had parallel, we had perpendicular, we had all different kinds of equation writing problems. What is it that tells us, even if we don't have a drawing, what one thing tells us that 2 lines are parallel if we graph them?
That they're opposite?
No, not opposite. Can't be opposite.
It's in my head. I just can't get it out.
Okay, what's the most common type of equation that we use for straight lines? There's only 3, guys. You forgot this already? Standard form, point slope, and what's the third one?
Slope intercept.
Okay, isn't that the most commonly used equation for straight lines?
Yeah.
Okay, so now if we have two parallel lines that are both in slope intercept form, what do we look at with those equations to tell us that they are parallel without even graphing them?
If the slope is the same.
The slope is the same, exactly. I'm not trying to complicate this, guys, but you already know this. The rule for parallel lines is that the slope is the same. So we can take that rule and apply it in proving that we have parallelograms, because it says opposite sides are parallel in the second method. For the first one, for congruency, we'd have to use the distance formula. How many times have you heard me say, you can't forget the stuff that you've already learned? It should be in your notes. You need to be able to go back and find it and use it again. Distance formula and slope equation stuff were in our initial definitions from the very beginning of the course. Remember, I said you don't have to worry about memorizing the distance formula. I have to look it up every time I use it. You're probably in the same boat, and that's fine. That's okay. So if the lengths of the sides are congruent, then we have opposite sides, then we have a parallelogram. If the slopes are the same, then we have a parallelogram. The third method is a combination of the two. So if you can prove that one pair of sides are the same length and the others are parallel by virtue of slope, you got it. And if you notice in the notes here, it doesn't give you these formulas. You know, in week 7, at this stage of the class, these should be in your notes already. You should be able to go, okay, I remember the distance formula. Where was that? Go back to the beginning. Day 1 definitions. 3 pages of them. That stuff has come up again and again and again. Slope formula, y2 minus y1 over x2 minus x1, right? The change in y over the change in x. Method 3 is just a combination of the two. And so these exercises, they're telling you how to solve these particular examples using the distance formula for the first one. First 2, actually. First one, you get some information that tells you that they are the same. You know, and you can see from the example, they don't even finish the square roots. Okay, who cares? It's going to be, they're not perfect squares, so they're going to be some crazy numbers with a bunch of bunch of numbers to the right of the decimal. Square root's the same, then they are the same. But you got to do that 4 times. If you think back to when we were doing the distance formula, and there's a problem on the slope test that asks you to find the perimeter of a triangle. This isn't any different than that. It's the same thing repeated several times. For a triangle, you got to do the distance formula 3 times because you got to do it for all 3 sides. Parallelogram's got 4 sides, so now you got to do it 4 times. Personally, I would never use the distance formula as a method for proving we got a parallelogram. I don't care which one you use. Slope's going to be easier. I don't have to mess with a square root. I don't like dealing with square roots. Slope formula is just adding and subtracting and then dividing. much more straightforward, less complicated in my opinion. And if the numbers don't match up, you don't have a parallelogram because the slopes are different. And the thing I like about these examples that the teachers put together here is there's a drawing that indicates what this parallelogram looks like, at least in the mind's eye of the person doing the problem. Really, really important. And it even has the little extra arrows here indicating the possibility that we have parallel lines. So I'm going to pause here for a minute, make sure you guys have time enough to get all of these.
Yeah.
So the next example gets into the properties of rectangles. Rectangle is a little simpler in some respects. It still includes all of the same properties of parallelograms. So you can't throw that information away. You have to remember it. You have to keep it handy. But now you also have to add 2 more properties. But they're going to help you also. The angle piece is the easiest part now, because now you know with a rectangle, all 4 angles are right angles. And you know that the diagonals are congruent. That's very helpful. And if you look at the examples below the properties, what's the formula that's being used here to figure out some of this information? Those first 2 problems.
A squared plus B squared equals C squared.
Yeah, it's the Pythagorean theory, exactly. And we can do that because the right angles. So if we're just looking to find this length here of SQ, which we kind of need to be able to figure out all the rest of these pieces. Okay, here's A, there's B. So SQ as the diagonal becomes the hypotenuse of your right triangle, because where's the right angle? It's right there. For that right triangle, SQ is the hypotenuse. So we can use the Pythagorean theory. And so all these examples are going to, again, it's the same kind of thing. Which property can we use to figure these things out? What about number 6 here? It says find EF. That'd be the same if it was a parallelogram or a rectangle, wouldn't it? Aren't those sides congruent? Yeah, of course they are, because the property tells us that they are. It's a rectangle is a type of parallelogram, so opposite sides are parallel, opposite sides are congruent. Easy. 3x plus 5 equals 7x minus 39. Figure out what x is, plug it into this part of the equation, 7x minus 39. That's what FE equals. Okay.
Can you go back to the definitions real quick? Cool.
So if you've already got the properties of parallelograms, all you need to do are add these 2 additional ones for rectangles. So the next shape is kind of a strange word. It's a rhombus. Rhombi, properties of rhombi, that's just a plural of rhombus. If you notice here, again, same properties of parallelogram. So those first 5 that we started with so far, they also apply to rectangles, and now you're seeing that they apply to rhombus, to a rhombi. Well, in the same way that a parallelogram is like a rectangle that's tipped over, a rhombus is basically a square that's been tipped over. So now you got 3 different additional properties for rhombus, but it actually simplifies things because now we know that all 4 sides are congruent, just like a square. The diagonals, nice to know actually that they are perpendicular. So when they cross here in the center, you got 90-degree angles all around this intersection here in the middle of a rhombus. So now you're creating all these right triangles in the center. Not only that, but the diagonals bisect the opposite angles. So diagonals bisect each other for a rhombus, and they bisect the opposite angles. So if we knew what this angle up here by J is, that diagonal there would cut it in half. So get those, add those 3 properties for your rhombus. And the last one is squares. Squares include everything, all those other properties. So if you didn't take any notes before, this should be written down somewhere. These first 5 here in this left-hand column, those are all the ones from parallelogram. The next 2, rectangles. The next 3, rhombus. That covers all of it. Questions, anybody? I'm gonna look ahead here real quick. Yeah, was that a question?
No.
Okay. All right, we'll stop on that today. So there's a lot there, obviously, in those first 4 sections: parallelogram, rectangle, rhombus, and square. We'll come back Tuesday, talk about special kind of parallelograms like trapezoids. There's also a graphic organizer that follows this. Let me see, let me rotate this. If you like graphic organizers, this is a really good one for all of these shapes. Haven't even talked about trapezoids yet. We'll try to cover that Tuesday. And then we have our last unit, which will be on circles. So this is unit 6. And the test on unit 6 will come out next week. So what I would encourage you guys to do is to work some of these problems. My view's off again. Got a study guide in here. Use the study guide to practice some of these things. like I've been recommending before, take a picture, send it to me. Say, hey, am I doing this right? What am I missing? There's no way in an hour and 20 minutes you guys can learn all of this. You're going to have to do some practice outside of class. Really, please do that. I want to see all you guys pass. So really would like to see some better scores on this next unit test. We've only got 2 weeks and we're done. School's out for the summer. According to Alice Cooper, school's out forever. Questions, anybody?
No.
Okay. Text me if you want to go over something individually.
Okay, will do. Bye, Jay.
All right. Thank you, guys. Appreciate you being here today.